Good evening, everyone.
Good evening, ma'am.
Good evening, ma'am.
Okay. So, how was your quiz too?
Ma'am, a little bit tiring.
Okay. Okay. So far, whatever topics we have covered, it is completely from linear algebra. The topics we are going to cover from today onwards is from a different topic, which is multivariable calculus. Okay. So here, whatever you have studied in math 1, so you have covered your in calculus you have seen functions of one variable and so many properties of such functions like differentiability, continuity, all those things you have seen for functions of one variable. Here we are going to look at functions of several variables. Okay, fine.
Ma'am, YouTube link for this session not updated in the Google Calendar.
Okay, no issues. I will post it here. Can you just hold on? I'll post it here. Just give me a minute. I guess the streaming is not working. Just a minute. I'll just see what is the issue.
Okay.
Okay, so I have informed about this issue. Anyway, this video is recorded. Meanwhile, someone is looking for the issue regarding live streaming. Okay. So, what is multivariable calculus or functions of several variables? Whatever functions so far you have seen, so in the Max 1 course, so what was the domain and codomain in that course? So usually F is from R to
R to
R,
R,
right?
ma'am.
Or
R to R.
take subsets of R as domain and codomain, right? So this is what you see in single variable functions, right? Or one variable functions. Okay. But whereas in the case of multivariable calculus, okay, here the domain and codomain both can be any Euclidean space Rn or Rm. Okay, so a scalar value. What is mean by a scalar? Scalar valued means your codomain is a scalar. Scalar means R, real number. Okay, so scalar valued means your codomain is a scalar, right? So it is a real number. So you see in this case, the codomain is just the whole R. Okay, whereas what is mean by vector valued? Vector valued means your codomain. I should not say codomain. An element of codomain is better, I guess. Element of codomain is a scalar. Okay, here your codomain contains vectors. Okay, vectors from Rn or Rm. Okay, in this case they have put Rm, so I'll also write Rm. Okay, so here scalar valued multivariable functions. The scalar valued multivariable function is a function f from the domain D, where D is a subset of Rn or the Rn itself. Okay, to R. Okay, and your n is greater than 1. Okay, multivariable means your n is greater than 1. You have more than one variable. Okay, same if you have vector variable function, the domain is having the similar property that you have a domain from Rn where n is greater than 1, and your codomain is also in Rm, your m is greater than 1. Okay, so remember in this course, mainly we are concentrating on the scalar valued multivariable functions, but it is good to know what is meant by vector valued multivariable functions. Okay. So there is no issue with the audio or anything else, right?
Yeah, ma'am.
No. Yes, ma'am.
Please repeat difference between scalar valued and vector valued.
Yeah, sure. See, for scalar valued multivariable functions, okay, scalar valued means what? A function takes a scalar value. So if you are taking f of some here you are taking domain in Rn, so some vector x. So this f of x is a scalar. Okay, and here this f of x, this is a vector. Okay, so f of x usually rise in the codomain, right? So here your codomain is a element of codomain is a scalar. It means your codomain is just the real numbers. And here your codomain consists of vectors. It means they are vectors from Euclidean space Rm. Okay, so this is the only difference between scalar and vector value. Let me give you some examples. Maybe it will help you to understand it better. Okay, so which of the following functions are scalar valued or vector valued multivariable functions? Okay, so first of all, they are giving that they are multivariable functions. It means the domain is anyway in Rn. Okay, particularly, can you say what is the domain in this case?
R2.
Two.
Yes,
Yeah,
ma'am.
in this case,
R2.
yeah, let me maybe write it commonly. So domain in this case is R2. And what about option 2? What is the domain?
R3.
R3.
R3. Option 3,
R3.
R3.
Again
Option
R3.
4,
R2.
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 okay, fine. Now, what about the codomain? What about the codomain?
Is R.
So you
R.
see x into y plus sine of xy. Is this a scalar or a vector?
Scalar.
Scalar.
When you substitute some values, it becomes a scalar, right? So this is a scalar valued function. Okay. And what about this one? A logarithm of x plus y plus z.
Scalar.
Scalar.
Again, it is scalar value, right? And what about this one?
Vector.
What is the codomain
Vector.
here?
R3.
R3. So this is the vector value.
Vector.
Okay. And what about this one here?
Also
Vector. R2.
R2. It is
R2.
again vector value, right? And what about this one? F of x comma y equal to xy? Again, scalar value.
Scalar
Okay,
value.
scalar valued means you know it is from R.
Ma'am,
So
is
the
it
codomain
necessary
is
vector
R.
having coordinates at least two coordinates?
Can you please be louder?
Ma'am, is it necessary that vector having a two coordinates, at least two coordinates, R2,
Yes, yes.
R3?
Minimum 2 should be there because your n is strictly greater than 1. So your n starts from 2. So minimum you need 2 for a multivariable function. Okay. Otherwise it
Okay.
is not multivariable. It becomes a one variable or single variable function. Okay.
Okay,
Fine.
ma'am. Thank you.
Means why x
Okay, ma'am.
square becomes a vector component in option 3?
In option 3, see, you see how many coordinates are there? 1, 2, 3. 3 coordinates are there.
Yes.
Right?
Yes.
So 3 coordinates are there means it is a vector valued function. Right? It is not just one single number. For example, what is maybe f of 1, 0, 0? What is f of 1, 0, 0?
1,
1,
0, 1,
1, comma 0,
1, 0, 0, right?
0.
Yeah. So you
0.
see, is this a
Yes.
number from real? Is this a real number or is this a value in R3?
Value in R3.
Yeah.
Value in
Function
R3.
maps R3 to R.
Okay,
This
okay.
function maps from R3 to R3.
Yeah, it is a mapping from R3 to R3. F is a function from R3 to R3. Okay. Fine.
Yes, ma'am. Yes, thank you.
Okay, ma'am.
Okay. Okay. So we have seen linear transformations. How does linear transformation, for example, T from maybe R2 to R or T from R2 to R3 to R2, something like this we have defined, right? How do we define T of x comma y? Okay, maybe is equal to alpha times of x. Okay, so this like this we have defined some scalar valued linear transformations, and here you see T of x comma y comma z is equal to x plus y comma maybe 2 times of z. Okay, so now you see that these are some linear transformations, and you see here the domain and codomain. You see it is so this is an example of a scalar valued, and this is an example for vector valued linear transformations. So all linear transformations are examples of all linear transformations where the domain is from a Euclidean space where the dimension is greater than 2. Okay, linear transformation with the domain Rn where n is greater than 1. All such linear transformations, they are multivariable functions. Okay. And what about polynomial functions? What is meant by polynomial functions? So f of x comma y, for example, x squared plus y squared. Okay. So you see this is a polynomial function. Now this is a scalar valued function. Okay. And what about f of x comma y or x comma y itself? I can put as x squared plus y, x squared comma y. Now this is a vector valued polynomial function. Okay, so f of x comma y equal to x squared plus y squared. You see this is an example of a scalar valued polynomial function. See, these are not linear transformations, right? Are they linear transformations? No, right? Because whenever there is a square term, it cannot be linear, right? So these are polynomial functions. Okay, there can be cube or any power of x and y. Okay, fine. It can be actually from R2, R3 or any Rn also. Okay. And what about combinations of arithmetic combinations or compositions? Arithmetic combinations in the sense that it can be sum of any two functions or difference of any two functions. Okay, or compositions. Compositions means you know, right? For single variable, whatever you did, the same concept is composition here also. So there are some rules, right? So suppose you have a domain in Rn and f is from D to Rm, it is a multivariable function. Okay. Same way you take another multivariable function g. Okay. It is also from E to Rp where E is a subset of Rm. Only condition here you should note that is that your E should contain the range of f. Okay. E should contain the range of f. This is the condition you need to note. Okay, if this condition is there, then you can define G composition F. Then what is G composition F? G composition F has domain of F, okay, and codomain of G. Okay, so G composition F has domain of F and codomain of G. So these concepts are just like whatever you do for one variable functions, the same concept. Okay. So just only difference is that here in this domain, here we are having vectors instead of just a scalar value. Okay. So G composition f of x is equal to G of f of x. So here for a vector, we are using this notation. This means that it is a vector, not a scalar. Okay. By using a tilde below, we are saying that it is a vector. It is just a notation. Okay. So now let us look at this function. If you have two functions f and g, okay, f is from R2 to R and g is from R to R. F is defined by f of x comma y equal to x comma x minus y and g of x is sin x. Now, which of the following option represents G composition? First of all, can you see what is the domain and codomain of G composition F?
R2 to R.
It is from R2 to R, right? Okay. Now, how to find this? G composition F of x comma y. This is the element of domain. It is equal to G of f of x comma y. Now, what is f of x comma y?
X minus Y.
Okay. And what is g of x minus y?
Sin X. Sin of X minus Y.
Sin of x minus y. Okay. So now which option is matching? Option 2. Okay. Is this clear? Okay. Fine.
Yes.
Now if two functions f from R2 to R and g is also from R to R, g is from R to R2. So you see that one f is a scalar valued function. What about g?
Vector valued.
Vector value. Okay. So can you tell me whether this function and this function are same or not? Are they same or are they representing different functions? Here t is
Same.
from R and here x is from R. Are they representing the same function?
Yeah,
Same.
same.
Same, right? So don't get confused by the variables and all. Okay, fine. So you have a scalar valued function and a vector valued function f and g. Now you have to do the same G composition F. Again, can you tell me what is the domain and codomain for G composition F?
R2 to R2.
R2 to R2. Okay. So now G composition F of x comma
Ma'am,
y.
how we are defining domain and codomain?
As I told you, for G composition F, it has domain of F and codomain of F. Okay, the domain of G composition F is the domain of F, and the codomain of G composition F is the codomain of G. So here you see what is the domain of F? R2. And what is the codomain of G? R2. So that gives you the domain and codomain for G composition F. Okay, fine. Is that okay? Fine. So G of f of x comma y. What is f of x comma y? What is f of comma y?
XY.
It is simply xy. So G of xy. Now what is G of xy?
e to the power
e raised to
E power t.
xy, comma e raised to minus xy.
Okay. So the option 3 is the correct answer. Okay. So far everything is fine, right?
Yes. Yes, ma'am.
Okay. So what are the arithmetic operations we can do for multivariable functions? Okay, so let us consider two different functions f and g, okay, which is having the same domain and codomain. Note that these two functions are having f and g having same domain and codomain. Then only we are defining these arithmetic operations. Okay. So you can define the sum as usual. F plus g of x is equal to f of x plus g of x for any x in the domain.
Ma'am,
Okay.
why domain and codomain be same for the
See,
arithmetic?
otherwise f plus g of x, suppose the domain of f and g are different, then you cannot what is f plus g of the same suppose this x is not there in the domain of g, but it is there in the domain of f. Is this really making sense to write g of x? It does not make sense, right? If x is not there in the domain of g, right? So an element, whatever you are considering, this should be there in both the domain of f and g, right? Okay.
Okay, ma'am.
Yes, ma'am.
And also why the codomain should be same? See, you are doing the addition of the images. So unless the elements are from the same codomain, this addition may not be even valid. Suppose one is from R2 and another is from R3. Can you add two vectors from R2 and R3? You cannot, right? So that is why you need the same domain and codomain. Okay, fine. So here the sum is as usual, and also the scalar multiplication. So c times f of x is equal to c into f of x. Okay, and when your codomain is m is equal to 1. So m is equal to 1 means what is the function we are considering? We are considering the scalar valued functions. When m is equal to 1, it becomes a scalar valued functions. So only for scalar valued functions we are defining the product. Okay, remember the product function is defined only for scalar valued functions, not for vector valued. Okay, so fg of x is equal to f of x into g of x. Otherwise, this what is mean by this multiplication is not defined. Okay, unless it is a real number. Okay, fine. And if m is equal to 1 and also your g of x is non-zero for x in the domain, then you can define the quotient f by g, which is f by g of x is equal to f of x by g of x for x in the domain. Here note that you should have a scalar valued function, and also the denominator should be non-zero. Okay.
Can you please repeat this point 3 once? I didn't get it.
Yeah, sure. See, in point 3, why we are particularly in point 3 as well as point 4, why do we need a scalar valued function? Suppose you are not having a scalar valued function, then what is mean by this multiplication will not be very clear. So for example, if you are having f of x and g of x, or suppose they are vectors, then what is mean by the multiplication of vectors? Vectors can be from Euclidean space, it can be matrices, it can be polynomials, it can be anything, right? There are so many different vector spaces. Sorry, not necessarily vector spaces, sorry. So many different vectors. So Rm means there can be possibility that R2 you can take means suppose x1, y1 and x2, y2. What is mean by multiplication of two vectors? We are only in Euclidean space. Here no vector spaces, sorry. So here x1, y1, x2, y2. So you are having two vectors from R2. What is mean by multiplication of two vectors in R2? It is not defined. That is why we are not considering this case. We are considering only when m is equal to 1. That is only we are considering the codomain to be real numbers. Okay, then only you know what is mean by multiplication of two numbers. Okay, same way for division also. What is division of two vectors? You don't know. What is mean by x1, y1 divided by x2, y2? We don't know. We don't have a specific definition for this. That is why this also we are not considering. We are considering again only codomain is R. That is scalar valued. We are considering both for point 3 and point 4. That is for quotient and product. Okay, is this fine? Okay, fine. Now,
it's scalar for the codomain, right?
Yes. For codomain, you are considering a scalar. Yes.
Okay.
The domain is
if
as
you're considering like R2 or R3 for the domain, it's not a problem. But for
it
the
does not matter because we are dealing with multivariable functions. The domain is from Rn. That is not going to change. It can be from R2, R3 or any Rn. That does not matter. Okay.
Okay.
Fine. Now look at this question. Let D be a subset of Rn and F is from D to Rm and G is from D to Rm. So F and G are having the same domain and same codomain. Okay, and they are multivariable functions on D. Which of the following statement are true? So the first one, the product function. So is it defined? Is the product function defined?
No, ma'am. M should be 1.
So here, what is the condition missing? So the product you see, it is defined only for scalar valued, I told. Here it is not mentioned that it is scalar valued, just they are putting some m. So this is true only if m is equal to 1, right? This is true only if m is equal to 1. So this is not correct. Okay, this condition is missing. M is equal to 1 is missing, so this is incorrect. What about the second one? The sum function, is
Yes.
it defined on D?
True.
Yes?
No, ma'am, not true because there is no mention. We cannot add two-dimensional vector to three-dimensional.
No.
We can
So
add, right?
it is just this definition is given here. You have two
Yeah,
functions
it's
f
true,
and g,
right?
and the sum function is defined. So that is what is given here also, right? What is the problem in the
Yes.
sum function? It is the same as we
It's
have seen
true.
above, right?
Yeah.
Okay. And what about the third option? How is the scalar multiplication of a function is defined for a multivariable function? C times of f of x is c into f of x. And what is given here? C times of f of x is equal to 1 by c times of f of x. Is that correct? Obviously not, right?
Not.
Okay. And if m is equal to 1 and g of x is non-zero, so they are defining the quotient function. So is this valid?
Yes.
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 Okay. Fine. Okay. So what are curves in RM? Okay. So whatever curves we have seen, generally we are.
Excuse me, ma'am.
Yeah.
Ma'am, when we are dealing with the point 3 and point 4,
Mm.
basically we are dealing with that we can multiply or divide only the scalar vectors, not the vectors in the R2 or R3.
See, here we are considering scalar multiplication for any vector valued functions. So it can be vector valued, or m can be 1, or any m can be 2, 3, or any rm. Okay. So scalar function. So the first two property, the sum and the scalar multiplication, this you can define for any vector valued function as well. Okay, that does not matter. So this option is, they are actually talking for any rm. But anyway, this c times of f of x should be c
No,
times
ma'am,
of
no,
f of
ma'am.
x.
I'm not asking for the question, ma'am. That the properties,
Yeah,
third,
so
ma'am.
here for this
We
two,
are
the domain and
keeping,
codomain both are vector valued.
yes, ma'am. We are
It
keeping
is
m
true for,
equal to 1 because we are dealing the values only from R.
no, this one need not be from m is equal to 1. This only for 3 and 4, you are considering
Yes,
m is
ma'am.
equal to 1.
I'm asking only for third and fourth point.
Yeah, for this two, you need m is equal to 1. Yes.
When we have to multiply two scalars vector or divide it.
Yeah.
Okay, ma'am.
Ma'am, can you just define what is S and V mentioning here?
I guess you
Yes.
missed the first part. So
Yeah,
the
yeah, I joined late due to some network.
SB means scalar valued. Scalar valued means the codomain is real number.
Oh, okay, okay,
Okay. Fine.
okay.
Okay. What are curves in RM? So far we know what are curves in R2. So whatever is curves in R2, you know that a curve in, first of all, let's see what is this definition saying. A curve in RM refers to the range of a function f from D to RM, where D is a domain in, here D is a domain in Rn. Okay. So D is a domain in Rn. Okay. So you see, you take any function of several variables. Okay. Whatever is the range, that range you call it as a function of, that range you call it as a curve in Rm. Okay. So for example, you see these functions here, like these are conics, you say. Okay. These are conics. Okay. All this parabola, circle, ellipse, hyperbola, these are all conics in R2. Okay. These are all conics in R2. So you see, you have f of x comma y. So this is a function of two variables. Here the domain and codomain. So you have f of x comma y going to R2. Okay. So these are conics in R2. And here you see helix. Helix, you see, it is obviously in 3D. So helix, it is in R3. Okay. And here you see it is from X comma Y from R2. Okay. From R2 to R2. Okay. Fine. So here you see, here R2 to R3. Okay. In general, see, just for visualization, what? Yeah.
Hello. Is there any particular name for the third curve?
Sorry.
Is there any particular name for the third curve?
No,
after
no, no.
helix?
Just I have given some function. No.
Okay.
Some function I have given. Okay. Fine. So generally, it is easy to visualize things in R2 and R3. That is why specifically here I am telling about this this line here. See, the graph of a function f of two variables. What is in one variable, we know very clearly. So two variable is what we can visualize. That is why I am considering this one particularly here. The graph of a function f on two variables is the set of all points x comma y, okay, comma f of x comma y. The third point is f of x comma y, where x comma y is in the domain of f. Do you remember how is the graph of a function of one variable is defined? It is x comma f of x, right? This is the graph of function of one variable, right? The same way, just a minute. Okay. The same way here, what is the graph of functions of two variables? It is a set of all x comma y comma f of x comma y. So this is what we are able to visualize. So when you are having more than two variables, we cannot visualize what is the image. Okay. So where x comma y is in the domain of f. Okay. So this creates whatever you see here, we call it as a surface in the space. Okay. We call it as a surface in the space. Okay. Fine. So a surface is also a curve. This is also a curve. So, but this graph particularly, they are talking as a surface. Okay. Fine. So there are few terminologies we need for the next concept. What are the few terminologies? So what is meant by a open ball center at A with radius R? Okay. So for example, first of all, let us look at R. In R, what is meant by an open interval? Center at A with radius R. What is meant by this in R? In real line, you take a point A, okay, and you consider A minus R and A plus R, but you don't consider this particular point. These 2 points are not included, right? These 2 points are not included for an open interval. Only this line, red line is there. These points are not there, right? So open A minus R comma A plus R. This is your kind of open ball at A with radius R. Okay, so this is in R. What about in R2? What about in R2? In R2, let us say you are having the XY plane. Okay, let us consider the origin. Okay, so this is your origin. Now, let us consider any circle. Okay, so the center is origin and the radius is R, and all the points, okay, all the points within this, excluding the boundary circle. Okay, here remember excluding the circle. Excluding, we are not including it, excluding the circle. That gives you the open ball. Here, for example, it is center at origin and radius R. Suppose you are having some other center and radius some other R. So this is another open ball. So remember, for an open ball, the outer points are not included. For example, if you are considering ball center at A radius R, where A is origin and R is 1. r is equal to 1. Okay. Is the point 1, 0 included in this ball?
No, ma'am.
Okay, your 1, 0 does not belongs to your open ball. Okay, so the whatever points lying on the boundary, that is a circle, does not belongs to this ball. The same thing in R3 you can imagine with a sphere. Okay, so it is a sphere with some center point and some radius r. Okay, and the outer sphere, that outer boundary will not be included. Okay, here you see you are having a strictly less than r. So set of all x in Rn such that norm of x minus a is less than r. Okay, so this is the open ball of radius r. So here whatever I have explained it for the usual norm. Okay, that is the Euclidean norm. Fine. So yeah, here they have given an example. So this is a ball center at x, radius r. Okay, and the outer circle is not included. Okay, and already you know what is the standard basis of Rn. These are some terminologies we are going to use for the next definition. For standard basis of Rn, the notation we are using is E1, E2, En. So this is the notation we are using. So Ei means, so it is 0, 0, 0, 1, 0, 0. So it means ith coordinate is 1. Okay, fine. So with this terminology, let us look at this definition: rate of change with respect to a particular variable at a point. Okay, already you have seen rate of change for one variable, right? In the case of one variable, how do you study rate of change? You consider some graph like this, right? You consider some graph. Okay, so you consider some point A, comma f of A. You want to find what is the rate of change of this function f at this point. Then what do? You draw a tangent, and then you take some point here. You call it some a plus h, comma f of a plus h, right? And then you make this h go close towards 0, right? For this you use so many secants, right? You take a secant and try to make this, bring the secant closer to this tangent by making h going to 0. So I'm giving a very rough outline of what you have done in the one variable. That is in your math 1 course, you would have seen this. Okay, so the same concept we are going to do for multivariable functions. You are going to have a function. Okay, and for this function, what is the rate of change with respect to a particular variable? Here there are more than one variable, so we are considering with respect to some particular variable at a point. Okay, so let us consider a function with n variables, f of x1, x2, xn. Be a function defined on a domain D in Rn containing a point A and an open ball around it. Okay, so remember you are having this point A such in this domain, and also it is containing having an open ball around it. For example, let us consider this point here. Okay, just in the case of one variable I'm saying. Okay, you are having this origin. Okay, f of x. Let us consider this function f of x. Okay, so is this function first of all defined at x is equal to 0?
No.
No, ma'am.
Ma'am, you're not audible.
Sorry, the call got disconnected. Am I audible now?
Yes, ma'am.
Yes, ma'am.
So till which point were you all able to listen?
The screen is not available. My screen is not visible.
Oh, sorry. Just a minute. So till I explained, gave an outline of the rate of change for one variable. Were you there?
Yes, ma'am.
Okay,
Yes,
fine.
ma'am.
Okay, fine. So let us consider, for example, f of x is equal to 1 by x. Is this function defined at this point 0, 0?
No, ma'am.
No.
It is not defined at the point 0, 0. Okay, fine. So now, for example, suppose let us say maybe some other function f. Okay. Maybe I am defining it as maybe square root of x. I am defining f of x is equal to square root of x. I am defining. Okay. So for this function, what is the domain?
Ma'am, positive real numbers.
Okay. So for all for this positive real numbers. Now you see for this point 0. Okay, can you find an open interval which is contained inside this domain? Can you find an open interval containing 0 which is contained inside the domain of f? No, right? You take any open interval containing 0, open interval, then that will not be inside this domain. Yes or no? You take any minus epsilon, comma, some 0 plus epsilon. Is this interval contained inside this domain?
No.
No, right? So that is what here they are saying, that you should make sure that whatever point you are considering here, that should have an open ball around it. Okay. So this is an important thing to define this. Okay. Why and how is this going to be important, that we are not covering in this course. But anyway, it is good to know that what is the meaning given for this sentence I am explaining. Okay. So you see that a point A you are considering and an open ball around it. Okay, that should also be inside this domain B. Okay, so then you are defining the rate of change of f at A with respect to the variable xi is limit h goes to 0, f of A plus hei minus f of A by h. So in case of one variable, how do we define? Limit h goes to 0, f of A plus h minus f of A by h. This is how we are defining in the case of one variable. In the case of multivariable, since we are considering any particular direction in which the rate is changing, you are considering that particular direction ei. Okay. So for example, if you are having the case of two variables, then E1 represents the direction of what? Direction of
X1.
x-axis. Okay. And E2 represents the direction of
Y-axis.
Y-axis.
y-axis. Okay. The rate of change in some particular direction. Okay. So that is what we are considering here. Okay. Fine. So I will give you some geometrical explanations in the next slide. So before that, just using the definition, let us see how to do this, solve this problem. Okay. Geometrically, I will give some more explanation when we are moving to the next step. So before that, let us see how to use this definition for solving this problem. Okay. What is the rate of change of f of x comma y comma z is equal to this function at 1 comma 2 comma minus 1 with respect to z? What is the rate? So first of all, what is the domain and codomain here?
R3, R32, R,
R2,
R.
R.
okay. So since it is with respect to z, so first of all, what is the standard basis here for R3?
1,
E1,
0, 1,
E1,
0,
E2,
0.
E3.
E3. Now, if it is with respect to z, then which direction you are considering?
0, comma 0, comma 1.
So for z-axis, you are considering E3, 0, comma 0, comma 1. Okay, so let us write the same definition here. So this is your vector A. Okay, so now what is the rate of change of f of x comma y is limit h goes to 0. F of your A is 1 comma 2 comma minus 1 plus h times of 0, comma 0, comma 1 minus f of 1, comma 2, comma minus 1. The whole divided by h. Okay. So now you see that this limit h going to 0. What is the sum of these two elements? They are just simple vectors. What is the vector addition of these two elements? Can you tell?
1, comma 2, comma minus 1 plus h.
1, comma 2, comma minus 1 plus h. Okay. And what is f of 1, comma 2, comma minus 1? Let's write in the next step. Okay. Fine. So this is limit h going to 0. Now what is f of, maybe I'll write in the next line. It's better. It's a lengthy expression. Okay. So now what is this limit h going to 0? What is the first expression? Suppose you are substituting 1, 2 and minus 1 plus h in this function. What is that you are going to get? Can you tell? 5 times of 1 minus 6 into 1 into 2 plus
3 into minus 1 plus z whole square
yeah
minus 2 into 2 into minus 1 plus h minus 1 plus h.
yeah. Okay. And
Uh,
f of 1, comma 2, comma 1 is,
minus 5.
so let me write maybe f of 2, comma 1, 1, comma 2, comma 1 separately. F of 1, comma 2, comma 1 is 5 minus 6 into 1 into 2. So minus 12 plus 3 minus 4. Is that correct? Yeah. So now this is,
Plus 4, ma'am.
Plus 4, ma'am.
is
Plus
it
4,
plus
ma'am.
4? So you
Yeah,
have
minus 1. We have minus 1 z.
1, comma, okay, sorry. It's minus 1. Yeah. So this is plus 4. So you have 9. And this term is actually becoming 0, right?
Screen is not visible.
But the session has over or it's been starting. Sorry?
Sorry, there is some power fluctuations here. Sorry. Am I audible?
Yes, ma'am.
Yes, ma'am.
Sorry.
Yes, ma'am.
Okay. So where were we? Yeah, so here, what was that? It is 9 plus 4 is actually 1, right? 8 plus 4, sorry. It's 0 only, correct. So f of 1, 2, 1 is 0. And then you see that what is f of this 5 times of the, let us simplify this term now. Okay, fine. So divided by h. Now if you are simplifying this, what is that you are getting?
5 minus 12 plus
So 5 times minus 5 minus 12 plus
minus
3 times of 1
3.
plus minus 2h plus h squared minus 4.
4
So minus 4 into
plus
plus 1,
4
so it's become
minus
plus
8
4. And then you
minus
have
4.
minus 4h divided by h. All right. And now here again you see that 5 limit h going to 0. So you have 5 minus 12 plus 3 minus 6h plus 3h squared plus 4 minus 4h by h. Now what is the sum of all these constant terms? You see 5 minus 12 plus 3, 8 minus 12, so minus 4 plus 4. So this sum of the constant terms is becoming 0. So what are the remaining term you have? Minus 6h minus 4h is
minus 10h
plus
plus
3h
3h
squared.
square divided by
Right?
h.
So limit h going to 0. So how do you find the limit of this term?
Ma'am, separate the terms.
You take h outside.
I will take out
So
the
you can take the h commonly and then you can write it as minus 10 plus 3h.
3h.
Because you can take this h commonly, so you can write it directly as limit h going to 0 minus 10 plus 3h. So what is the answer?
Minus 10.
Minus 10. All right. Okay. So
Ma'am, for this question, if I like differentiate with respect to z, keeping x and y constant, and then put the value, I got the same answer. So is it the correct way to approach this question, or like go with this long method?
This is basic definition of differentiability, I think.
No, I just differentiate with respect to z, and
Yes, yes, you got the same answer.
yeah. So can I do that, or am I
Yes, yes,
wrong?
we can.
Hello, ma'am. Ma'am, you
Ma'am,
are not
your
audible.
mic is off. I think we can do in that way also.
yeah, you can do it in that way as well. Yeah, it is fine.
Okay.
It is correct.
This
Whatever
is
you
a conventional method. This
like you are
is
finding the partial derivative actually and then computing it at this specific point. Yeah, that also works fine. Okay,
yes,
that is
this
what
is
we are going to see next
yes.
actually. Okay.
Okay. Thank you,
This is
ma'am. That's
conventional method. I
yeah.
think.
Sorry.
This is a conventional method.
Yeah, this is it's not exactly conventional method. This is using this particular formula. Okay, but you see that this formula is just same as whatever you are doing. That is finding the partial derivative with respect to z and then applying it at that point. So that is also fine.
Okay,
Okay.
ma'am.
Okay, ma'am.
Okay. So now suppose f of x comma y comma z is equal to xy plus yz plus zx minus 3xyz, which is a multivariable function defined on domain D, which is in R3. So domain is given. Can you say what is the codomain?
R.
R.
Okay, so your codomain is R. So f is a function from R3 to R. Okay, so f is a function from R3 to R. So what is the
Scalar
first
valued.
option? Is it correct?
Correct, ma'am. Scalar valued.
F is a scalar valued multivariable function. The rate of change of the function f at 0, 1, 1 with respect to x is 1. What about this point?
-1, I think, should be the answer.
No, ma'am, it's wrong.
It's wrong.
1, 0, 0.
So you need to compute it in this case. Actually, it is not straightforward. You need to compute it and then find it. Okay. So when you are computing it, what is it you are getting?
2, no?
-1, I think.
-1.
-1. Ha, 2 -1. 3. -1.
Yes,
-1.
-1.
So actually, when you are doing the partial derivative with respect to x, then you will actually write, I have not even started it, but if you can do it, you can use this formula straight away and the substitute. Otherwise, you have to do this using this formula, which is actually quite lengthy. So if I'm doing this, let's see how far you all can understand. If not, I will explain this step. So when you are finding the derivative with respect to x, you need to keep y and z as constants. Okay, keep y and z as constants. So if you are considering y and z as constants and then finding the derivative of this with respect to x, what is the answer you are getting?
-1.
Y?
Sorry. Y plus
Yeah, y.
Z plus
And
Z.
yz is a constant plus
Z
z
minus 3 YZ.
yz. Okay. Now at the point 0, 1, 1. What is the answer you are getting?
1 plus 1 minus 3. -1.
1 plus 1 minus 3. So the answer is -1. So option 2 is
False.
not. Okay. What about this one? So dou f by dou x. So this step, is it fine for everyone? Whatever I have written? Is it okay? How did I do this derivative?
Yes, sir.
Is it okay?
Yes, sir.
Okay, fine. So next step also the same. But now this time I'm going to find the value at 2, 2, 2. So the same y plus z minus 3yz at the point 2, 2, 2. Okay. What is the answer? It is 2 plus 2 minus 12.
Respect to Z.
With respect to x is same as the function of 2, 2, 2 with respect to z. So first I'm computing with respect to x. All right. Fine. So
Minus
2 plus
8.
2 minus
8.
8. Yeah. Answer is minus 8. Now let's find what is dou f by dou z at the same point 2, 2. So what is the derivative of this
Y
function
plus
with respect
X.
to z?
Y
So
plus
first
X
xy becomes, so in this case, what are the things you need to consider as constants?
Y, X and Y.
So you need to keep x and y as constants. Now you see that dou f by dou z, here it is,
Y
first term is 0 plus y plus x
minus
minus
3xy.
at the point 2, 2, 2,
It is
which
same.
is again the same. So option 3 is correct. Okay. What about the fourth one? The rate of
It's correct.
yeah, change of the function f at 1, 3, 5 with respect to y is -9. Okay. So dou f by dou y. So what are the things you need to consider as constants here?
X and Z.
Keep x and z as constants. So what is the answer here? So let me scroll up. So here x, y. So you just have x and then you have y, z. So just z and then zx. So you have 0 and then minus 3 xz. Okay. At the point 1, 3, 5.
Excuse me, madam.
Yeah.
6 minus
Somebody is
15.
alerting that it is not getting recorded.
Sorry?
Somebody is alerting us saying that the session is not getting recorded. Is that so?
The session is recorded, but it is not streamed.
Or is it?
Okay. So this once this session is over, I will post this. I will send this recorded thing, and they will do the streaming. It is not live streaming, but it will be streamed later. Okay.
Wonderful. No problem. Thank you.
Okay. So the answer here is 1 plus 5 minus 3 times of 1 into 5. So you get 6 minus 15, which is minus 9. So the option 4 is also correct. Okay. So this problem is fine for everyone, right? Whatever we have done here. Okay. Fine.
Ma'am, can I ask one question?
Yeah, sure.
Ma'am, it's not related to this. It's in activity 1.
Hmm.
In activity 1, question number 3. I'm not
Is it
getting.
related to this topic, or
I think the topic is already covered. That's why.
maybe then we will do it at the end. Okay.
Okay.
So because
Ma'am,
we are
one more question in related to like you taught about open ball. There was a question about ellipse in 9.1, like f of
okay. Then whatever questions you have, we will do it at the end of the session. Is that okay? Okay.
I think that is related to this.
Yeah, I understand, but let us
Let's
do
cover
the
the
questions at the end. Okay.
Okay,
So
okay.
the flow will not be interrupted. Okay.
Okay, ma'am. Okay.
Fine. Okay, as I told you, I want to give the geometrical explanation of what is happening here. Okay, so what is the partial derivative f of x comma y with respect to x at x naught comma y naught? Okay, it is easy to visualize in this case. That is why I'm considering the 2 variable case. So that is what is extended for n variables also. Okay, so as I told you, the graph of a 2 variable function is in 3D, right? So you see that you are having a graph in 3D. Okay. So now you see that here, let us see, you are having some 3-dimensional structure here. Okay. And you are considering some point on this surface f of x naught comma y naught. Okay. On this surface, you are considering one particular point and you want to find the partial derivative of this function at this point with respect to x. Okay. It means what we are doing, we are considering, okay, this y value as a constant. Okay, it means what, we are fixing this y value, okay, and just varying this x. So it means what is happening, this particular slice, if you are considering, this is the curve we are considering. Okay, so this is the curve we are considering. You see, this is actually, this is your point y naught. So your y naught, the value of y is fixed. Okay, only the value of sorry. So yeah, so this is, yeah, correct. So this is your y naught. So at this y naught, it is fixed. Your y is not varying. So this curve, at this point, your y naught is, y value is fixed. So what we are changing is only the x value. So as the x value changes, this is what you are getting. Okay, so only your x values are changing and your y value you are fixing. So this part we are not moving anywhere. Only at this point we are here. We are not moving anywhere along the y-axis. We are moving only along the x-axis. Okay, so you are considering now this as a function of x with keeping this y naught as a constant. Okay, now this is considered as a function of x with respect to y naught, and then you are doing the calculation of this derivative as usual. Okay, so what is your dou f by dou x at this point x naught comma y naught? Okay, it is simply the derivative df by dx. Okay, so it is simply the derivative df by dx at your point x is equal to x naught, and you are actually fixing this y value. Okay, y is equal to y naught. So it is you are basically fixing this value of y. So you are considering this only as a function of x. So you can write it as a same definition as you are writing for the derivative of a single variable function. Okay, the same you can do when you are considering the derivative with respect to y. Okay, the same can be done when you are considering as a derivative with respect to y.
Madam,
So
how is this
actually
x
here
is
I
equal
can
to-
write it 1 minute. Here I can actually write d by dx. So this is confusing, right? So better I'll write it here f of x comma y naught. This is a function of one variable at x is equal to x naught. It is better if I write it this way when I'm writing the normal derivative. Yes, now what is the question, please?
No, I was just saying, since we are fixing y at y naught, and the y naught, the y being fixed here, then we should find out x is equals to x, no, xi, something like that.
X is equal to x I.
I, yeah, because that's a variable that's changing, no?
No. Your variable is not changing. So here x is your variable. So that is why this is the derivative of the function f of x, where your y is some fixed number. Okay. At the point x is equal to x naught. Okay.
Okay.
So now your f of x is the function where y naught is considered as a constant. Okay. And then once you find the derivative with respect to x, keeping this y naught as constant, after finding the derivative, you simply substitute x is equal to x naught. That is what we are doing in partial derivatives, right? Okay.
Ma'am, can you explain this graph again?
See, what is that happening when you are having a three-dimensional structure like this? It is actually it is a surface. It is a surface means it is a function of x comma y. Okay. Now on this graph, you are considering a particular point here. Okay. When you are considering this particular point, so this point is actually f of x naught comma y naught. Okay. So now this particular point, now you want to do the derivative at this point with respect to x alone. So it means you are fixing your y value. So fixing the y value means this is the y value and I have fixed it. Okay, so I'm not moving anywhere along the y axis, but I am allowed to change the values of x. Okay, so it means you are considering this as a function of x, keeping your y value constant, which is y naught. Okay, you find the derivative of f with respect to only x. Okay, and then after finding the derivative, you simply substitute what is the value of x equal to x naught. That's all. Okay. For example, if you are having f of x is x comma y is equal to some x squared plus y squared. Just some example I am saying. Okay, suppose you are having like this. Then what is happening is that, and you are finding the derivative at some point, let us say 1 comma 1 or something like this. Then what you are doing, you are considering this function. Okay, I am substituting the y value first. And then I am finding the derivative 2x plus 1. And then I am substituting the 1 value here. Okay, so you are finding the derivative f dash of x. Okay, and then I am substituting this 1 value here. Okay, that is what is happening here. Is this fine?
Yes, ma'am. Fine.
Okay.
Yes, ma'am.
Okay, now the same thing is happening when you are having doing the same with respect to y also. You look at this graph. In this graph, what is happening? Just observe it for a moment. So what is going on here? Here the same thing we are doing. Only thing here you are fixing your x naught and you are varying your y. Right? You are fixing your x naught and varying your y. See, you are now taking this this plane along this line. So here you see your y x value is fixed. Okay, so x value is fixed. You are not moving anywhere along this line x. It is fixed. Only at this point you are considering this curve, and you are moving along y. Okay, so now you are considering this as a function of y and then finding the derivative. This is what we are doing for partial derivative. Okay, so here it is actually d by dy of f of x naught comma y at y equal to y naught. Is that fine? Is this fine? Okay. Okay. So in general, you in one dimension, what do? You take a curve, you consider a point, and to find the derivative, you take this tangents and move it along to bring it to this tangent, right? So just to explain that, this graph is given here. Okay. So here what is happening? So you see that, for example, if it is dou f by dou x at x naught comma y naught, it is nothing but limit h going to 0, f of x naught plus h, comma y naught, minus f of x naught, comma y naught, right? What is this correspondingly? This is your f of a plus h, right? And this is your f of a. And then in the new denominator, you have h. All right. So here your a is actually x naught, comma y naught, and your h is actually the direction of x axis. So it is 1, comma 0. Okay, h times of 1, comma 0. So here it is f of a plus h ei plus f of a. That is what we have defined in the rate of change definition. So I have just given it straightforward here. Okay. So this is with respect to x. Same you can do with respect to y also. This figure particularly is given for with respect to x. Okay. Fine. Now,
ma'am, in the previous example, can you go there for a second?
Here?
No, the previous one.
Yeah.
Here in partial f by taking z constant, why 0 has come in the, I couldn't understand that.
Here?
It should be y, yeah.
See, in
Should it
other
not
terms
be-
also 0 is there. I just did not mention, and here I have mentioned. See, here also you see that. Here also you see that when I'm doing this dou f by dou x, when there is yz, okay, when there is yz is a constant. So the first term x into y, it is y, and the second term is actually 0 because it is just a number and the derivative of a number is 0, right?
Okay.
The same thing is happening when you are considering with respect to z. It is actually happening in the very first place itself. It is x times of y. So x into y, x and y are constant. So it is also constant. So the derivative of a constant is 0.
Okay.
Okay. And when you are considering for y, which term will become 0 when finding the derivative? This term. The third term is actually becoming 0.
Okay.
Is it okay?
Yes, yes.
Okay. Fine. Okay. So the derivative, partial derivative definition, it is given now. Let f of x1, x2, xn be a function defined on domain D in Rn. The partial derivative of f with respect to xi is a function denoted by f of x with respect to xi, or dou f by dou x xi x for x at x, and defined as dou f by dou xi at x is equal to limit h going to 0 f of x plus h ei minus f of x by h. Okay. So for example, in this case, it is along x. Okay. Along x means what is the corresponding standard basis element? E1, right? It is E1. So when you are having x naught, comma y naught, okay, and then plus h E1, it is actually h, comma 0. So that is why I have straightforwardly written it as x naught plus h, comma y naught. It is the same. I have written it directly. Okay. So this actually reduces to this term. So when you expand this and write, this is x is nothing but x1, x2, xn, and ei is the ith term is 1. The other ith coordinate is 1, and the other terms are 0, and f of x1, x2, xn. And now when we are adding these two terms, you see that in the ith position alone, you are having xi plus h. In the ith position alone, you are having xi plus h. And all the other terms are just the same. Okay? Fine. To calculate the partial derivatives with respect to xi, you have to consider this f as a function of xi and all other variables as constants, just like we did in the previous example. Okay? Fine. So here for this example, let f from R2 to R be defined as f of x comma y is equal to x cube plus 3xy. Identify the correct option with respect to the partial derivatives. Okay. So for exam purpose, you can of course do it using the definition, straight away formula. Just for the sake of you to get to know with the examples, I want usual definition with whatever definition we have used above. I am going to do this problem only with the definition which is given above. Okay, shall we do that only with the definition given above?
Yes, ma'am.
Okay, fine. So now what is this function dou f by dou x with respect to, let me write the definition here. So dou f by dou xi at x1, here you have only two variables. So I write maybe I can, yeah, x1, x2, okay, is limit h going to 0, f of x. So if it is x1, then it is going to be x1 plus h comma x2 minus f of x1 x2 the whole divided by h. If it is for x2, then it is going to be limit h going to 0, f of x1 comma x2 plus h minus f of x1 x2 by h. Okay, so let us use this definition and see what is your dou f by dou x and dou f by dou y. Okay, so your dou f by dou x. Okay, so what is this becoming? Limit h going to 0. So you have your f of instead of x you have x plus h the whole cube minus 3 times of x plus h times of y the whole divided by, and here you also have,
That is plus, right? X cube plus 3xy.
minus f of x1 minus x2, right? x1 comma x2, right?
No, for the first term, yeah.
Oh, here, yeah. And minus x cube plus 3xy or minus 3xy. Okay, whole divided by h. Okay, so here when you are expanding this definition, what is the formula for x plus h the whole cube?
X cube plus h cube plus 3x square h plus 3h square x.
So plus 3xy minus plus 3hy minus x cube minus 3xy divided by h. Okay, now what is the value? So x cube and x cube gets cancelled, and h cube, sorry, not h cube, and 3xy and this gets cancelled. Now in the remaining term, we can take the value of term h alone commonly, and then what is the remaining term? H squared plus 3x squared plus 3xh plus 3y whole divided by h. So when you are now substituting the making the h going to 0, what is the answer you will get?
3x square plus 3y.
Is this matching with your usual derivative formula dou f by dou x? If you are doing, will you get the same answer? You will get 3x squared plus 3y, right?
Yes.
Okay.
Yes, ma'am.
Okay, so fine. So this now, what is dou f by dou y? Can we straight away write it without using the formula? Dou f by dou y, what is the answer?
3x.
3x.
So it is simply 3x. Okay, you can
3x.
verify it using this formula also. Now dou f by dou x and dou f by dou y values we are having. Now what is the value at one? Let me write it maybe here. Fx, fy at the point 0, 0, 1, 1 and 1, 0. What are the values of fx and fy? Just tell me. At 0, 0, what is the value of fx?
0.
Zero.
0.
It is 0. And fy value?
0.
0. And 1, 1, what is the value?
6.
6. And here?
3.
3. And 1, 0?
3.
3.
3.
3.
So now look at the statements. Dou f by dou x at 0 and 0, they are equal. True, right?
Yeah, the first option
The
is
first
incorrect, right?
statement?
Incorrect.
Incorrect. And second one,
Incorrect.
third one,
True.
Correct.
and fourth
Correct.
one, dou f by dou x. It is not +3, just +3. You have, so here you have 3x squared, here 3x squared plus 3y. Anyway, this is also incorrect, right?
Wrong. Yeah.
Yes, ma'am.
Okay. Let f of x comma y is equal to xy by x squared plus y. Identify the correct options with respect to the partial derivatives of f. How do you do this? So you are now having the form of
U by V.
u by v. So when you are having the u by v form, how do you do that?
Partial derivative of u times v as partial derivative of v times
du
u.
dash. The general derivative formula I am writing, you can do the same for the partial derivatives as well.
Minus
Dash minus
U
v dash.
V by V square.
Okay, this is what is the usual derivative formula. The same we can use for partial derivatives as well. Okay, now dou f by dou x, what is that equal to? So you have to consider, remember, you have to keep y as a constant. Okay, if you are forgetting this, better write it every time. Okay, so now what is happening here? You are having v is x squared plus y and your u is xy. So with respect to x, when you are differentiating, what is it you are getting? What is your u dash with respect to x?
Y.
Y.
And minus, you are keeping your u term straight, just as it is. And then what is your v dash?
2x.
2x. The whole divided by your v squared, which is x squared plus y the whole square. So what is the answer? X squared y plus y squared minus 2x squared y. The whole divided by x squared plus y the whole square. Okay. Now this is y squared minus x squared y by x squared plus y the whole square. Okay. So first of all, the first statement they are asking is dou f by dou y are not defined at 1, 0. So for this, do we even need to calculate all this? Do we need to calculate all this, or straight away can we answer this?
Straight away we can answer because it is 0 by 0.
Yeah, you see that. First of all, it's the point there in the domain of the function given to you.
Ma'am, it's 0,
no.
0. So the equation is going to be 0 anyway.
No, what I'm asking, first of all, is this 0, 0 there in the domain of this function?
No, ma'am.
No, right? This function is not defined at 0, 0, right? Okay. So in that case, you can straight away write this is not defined at 0, 0. It is fine. And also the partial derivatives, you see that anyway, it is not going to be defined. But you don't have to go to this step to write this. You can straight away look at this function. The function itself is not defined at 0, 0. Okay. So this option is correct. It is not defined at 0, 0. Okay. Fine. What about the option 2? So for option 2, you also need dou f by dou y. So let us do dou f by dou y as well. So now what is your constant?
X.
This is your
X.
Okay. Now, when you are doing dou f by dou y, what is the derivative?
X square plus y square.
Square plus y v into u dash is x.
Y square, ma'am.
Xy into 1.
Y square.
Yeah.
So here you have x cube plus xy minus xy by x squared plus y the whole square, which is just x cube by x squared plus y squared the whole square. Okay?
Ma'am?
Yeah.
That will be x square plus y square, ma'am.
Where?
No, x square plus y.
V.
Yeah.
V.
For this term you are telling?
Del f by del y.
Last row
V.
denominator.
Del f by del y. V. X square plus y
Your
square.
v is x squared plus y, and then your u is xy, and with respect to x it is with respect to y it is simply x, and then
Yes,
minus
ma'am.
u is xy, and your v is x squared plus y. Your x is constant, so x squared term will become 0, and the derivative of y with respect to y is 1, right?
And the last answer and the last step, x cube by x square plus y the whole square.
Oh, the last step you're saying. All right, all right. Thank you, thank you. Yeah, so this is the answer for dou f by dou y. All right, now you have to find the values of these functions at 1, 1 and 1, 0. So fx, fy at 1, 1 and 1, 0. What is the answer?
0.
So at 1, 1, the value is 0. And what about for fy?
1.
1, 4. Right? Not 1, 1 by 4.
1 by 8.
1 by
Not
4.
8.
Yeah.
So 1, 1, so 2 squared is 4. And 1, 0, when you are substituting, what is that you are getting? Again,
Minus
it
1.
is 0.
0.
And here,
1.
1. So now let us compare with the options here. So dou f by dou x at 1, 1 is 0, and dou f by dou y 1, 1 is 1 by 4. So this option is correct. So this option is incorrect. And dou f by dou x at 1, 0 is 0, and dou f by dou y at 1, 0 is 1. So this option is also fine. Okay. Fine. So up to this, is it clear for everyone? Yeah?
Yes, sir.
Okay, fine. Okay. So now you see a function here. So what is this type of functions called?
Partwise.
Piecewise.
Piecewise. Piecewise.
Okay. So piecewise functions means the functions are defined for different pieces. So here, since we are dealing with multivariable functions, these pieces are representing any part of your domain. Okay. So here they are considering all non-zero vectors and a zero vector. Okay. Sometimes it can be maybe from the unit square it is defined in a different way. Outside the unit square it is different way. Something like that is there, but it is very rare. Okay. So this is a piecewise function. So how does the piecewise function, we have to, what is the value of f of 0, 0?
0.
It is simply 0. You should not use this xy by x squared plus y squared for f of 0, 0. Okay. What is the only difference between this function and this this function at the point 0, 0? Can you say? This function f of x, y equal to xy by x squared plus y, is this defined at 0, 0?
No.
This is not defined. But what about this function? Is this defined at 0, 0?
Yeah, it is defined.
It is defined. So by this way, you can define when piecewise functions helps us to define at some specific points. Okay. So now you see that f of 0, 0 is defined. Okay, and it is specifically 0. Okay. Now what is the partial derivative?
Sorry, ma'am, can you
Yeah.
please describe this thing again once, please? I just
So in the previous function, what were you having is that you are having f of x, y is equal to, what was the function? xy by x squared plus y. Sorry. xy by x squared plus y. Okay. Now you see that this function, okay, this is not defined at 0, 0. Right? When you put 0, 0, is this function defined? No, right? But now look at this function. At 0, 0, specifically they have defined it to be 0. Okay? Specifically they have defined it to be 0. So you see that f of 0, 0 is equal to 0.
Okay, so just because that condition is given, that's why we are saying.
Just because you have this extra condition, it is defined at 0, but this one they have not given any condition. So this is not defined at 0, 0.
Okay.
Okay, fine. Okay, so now in this case, remember when you are finding partial derivative for piecewise functions, remember for finding partial derivatives of piecewise functions, find the partial derivatives for each piece separately. Sorry, each piece separately. Okay, so it means what? When x comma, for this particular example, when x comma y is not equal to 0, 0, you have to find the derivative separately. And when x comma y is equal to 0, 0, there you find the derivative separately. Okay, so this is how you are doing the partial derivative for piecewise functions. For example, the simple one variable function also, suppose it is a piecewise function. Suppose you are having x squared when x is greater than 0 and 0 when x is equal to 0 and maybe minus x when x is less than 0. Something like this is there. Then how do you find the derivative? The same way you have to find, right? F dash of x, you write it as 2x mainly for x greater than 0, 0 when x is equal to 0 and minus 1 when x is less than 0. This is how you find the derivative for piecewise function of a single variable function also. The same you are doing here. Okay, remember you should not write the derivative in one step for a piecewise functions. Do it separately for each piece. Okay, is that fine?
Yes. Which means we are not doing the way we have done in the previous exam.
No, here you have to first do it for x comma y not equal to 0, 0, and then you have to do for x comma y equal to 0, 0. The same method, but for this piece first and then this piece next. Okay.
So for the first xy is not equal to 0 to 0, we will do the like we have done in the previous
exactly,
question, right?
exactly, yes.
So we will find the del f by del x, keeping y constant and so on and so forth.
Yeah, so for this you use the same technique like you used in the previous method, and this for x comma y equal to 0, 0, only for this maybe we need to use the definition of partial derivatives. Okay.
Okay. Okay.
Fine. So let us continue. So now what is dou f by, let us first fix the piece which you are considering. You are considering at x comma y is equal to, not equal to 0, 0. Okay. So now for this one, what is your dou f by dou x? Your dou f by dou x is, as usual, you are having a u and v. So if you are having a u and v, then it is x squared plus y squared the whole square, and then your v into u dash
x square plus y
plus
square
y square
into y. Into y.
sorry yeah, so x squared plus y squared, and with respect to x it is y, and minus v u dash minus u into v dash. V dash is 2x. So what is the answer? X squared y plus y cube minus 2x squared y, the whole divided by x squared plus y squared the whole square. Okay, is it okay? This further we can simplify. So this is your dou f by dou x. Now what is your dou f by dou y? You have to do it in a same way. Dou f by dou y is equal to v. What is your u dash?
x.
and u into v dash. What is your v dash?
2y.
Okay. So now this you see that here it is x cube plus y squared x minus 2xy squared the whole divided by x squared plus y squared the whole square. So if you have some confusion in this kind of terms, just look at the powers of x and y. So here the power of y is 2 and the power of x is 1, and the same is for this term also. This is actually having the same powers for x and y. So you can add and subtract these terms. So what is that you will get? X cube minus xy squared. Is this step okay? It's not any big thing. Just you have to look at the coefficient, powers carefully.
In the previous step, it's y cube minus x square y. The above that.
Here,
Yeah.
y cube minus, yeah, 2 is not there. Minus x squared y. Thank you. So you have got dou f by dou x as well as dou f by dou y. So this is done for which part now?
Not
You have
equal to
done
0.
this for the part when
equal
x comma y is non-zero. Now you have to look at what is happening when x comma y is 0, 0 separately. Okay. So now what is dou f by dou x at 0, 0? Using the definition, how do you write? It is limit h going to 0 f of h comma 0 minus f of 0 comma 0. Is that correct? So you see that with respect to x means what do you write? With respect to x means here what do you write? You have the point 0 comma 0. So it is actually the steps if you want to see. It is limit h going to 0 f of your a is 0 comma 0 plus h times of e1. E1 is 1 comma 0 minus f of 0 comma 0 divided by h. So this I have written as f of h comma 0 minus f of 0 comma 0. Okay. Now what is f of h comma 0? What is f of h comma 0? You have to use the
0.
definition. 0. So f of h comma 0 is 0. 0 comma 0 is 0. So the numerator is 0. So before even applying the limit, this term is becoming 0. Okay. So you see that dou f by dou x at 0 comma 0 is 0. You should write it in this method. Okay. And dou f by dou x, dou y at 0 comma 0. What is this limit? H going to 0. Can you tell what is the expression I should write here?
F of 0 comma h.
Okay. Again it is
0.
0. Okay. Remember you should look at it from this expression either or you use the definition, but you should not put 0 comma 0 in these expressions. Don't do that mistake. It is okay to use whatever expression is given here. It is okay to use this particular expression, or you can directly do all the steps like I have done here, but never put 0, 0 in these expressions you have found for x comma y not equal to 0 comma 0. Am I clear?
Yes, ma'am.
If the function itself is given as 0 at 0 comma 0.
Write it straight away as 0, yeah.
Yeah. Okay.
But sometimes if it is not 0, you should not straight away use this and put 0, 0. You should do these steps here. Whatever the partial derivatives you use, you should use that. That is why I have given the steps here. Okay.
Okay. In case if it was given as 5x square, something like that.
Yeah, some other function is there, then you should do the partial derivative separately for
It's the
this
same steps, right? I mean, like what we have done for not equal to 0, we'll do the same thing.
It is better you use this limit formula because you see your x comma y is now 0
Oh,
comma
0,
0.
0. Okay.
It is always recommended you use this these steps when it is particularly 0 comma 0. If it is some other piece, then it is different. But here specifically your vector is only the 0 vector. That is why it is recommended to use this formula here. Okay.
Okay.
Fine. So a simple formula problem here. Let f from R2 to R be defined as f of x comma y equal to x squared plus 4xy minus y squared. Suppose dou f by dou x is equal to dou f by dou y at this point 12 comma k. Find the value of k. So it is very simple. What is dou f by dou x?
2x plus 4y
2x
plus 4y.
plus 4y. And what is dou f by dou x at 12 comma k?
24
2
plus
into
4k.
12 plus 4k, right? So it is 24 plus 4k. Now what is dou f by dou y?
4x minus 2y.
4x minus 2y. So at 12 comma k, what is your dou f by dou y?
48 minus
48
2k
minus
minus
2k.
2k.
All right. So now it is given that these two terms are equal. So it means you write 24 plus 4k is equal to 48 minus 2k. So this means what? 6k is equal to 24. So it means your k is equal to 4. Is this fine? The usual derivative only, but just that they are giving some conditions and asking you to find the constants underlying. Okay? Is this okay?
Yes, ma'am. This is fine.
Okay. So the next question
Ma'am,
is again a very simple. Yeah.
I'm just a moment. Like this session is being recorded, right? Will it be uploaded on the calendar? Like
It will,
I have
yeah,
a doubt
yeah,
on the
yeah.
prior
You
portion.
can watch it in YouTube later on. It will be streamed later on. Okay?
Okay,
Don't
fine.
worry.
It will be uploaded.
Will
Okay,
it
ma'am.
be
Fine.
by tomorrow or day after tomorrow?
By tomorrow, it will be there.
Okay.
Ma'am, like I have one small doubt. If it's short, you can just explain now. If not, then I can. If it's there in the previous portions, I can watch it later. Just the directly finding the partial derivative way is there, right, ma'am?
Yeah.
Like so Sarang sir like mentioned in his last lecture that it cannot be used while one particular condition, but most of the questions you won't be facing like that. He said like that. So what is that one condition? I didn't get that particular condition. Like
Did he
where
mention
should
any
we?
condition?
Actually, I couldn't find any condition on that video.
I guess he is mentioning the condition like we saw in this case. So in this case, as I told you, since it is only for this particular 0, 0 vector, finding the partial derivative straight away, it is recommended to use this formula rather than finding it straight away. Okay. Here it is 0, so it is okay.
Like-
but if it is some other function, it is recommended that you use the formula rather than the straight away partial derivative formulas. Okay.
So like if given like two conditions in that cases, right?
Yeah, when you are having a piecewise function. Yeah.
Okay, fine. Thank you, ma'am. Thank you. Yeah.
Okay. So far, I know this is the only place where you have some difficulty in using the
Yeah,
direct
you should
method.
use the okay. So we should use the method like this.
Yeah.
Fine. Like this one I'm not so familiar with. The direct version I'm familiar with. So that's the reason. Like so I have
See,
to
I
learn this.
always
Okay, fine,
recommend
yeah.
that don't restrict yourself to only the direct method. Please do
Mhm.
some problems. Let us say you have done some, for example, this problem itself. This is a very big problem, right? This you have used
Yeah.
the definition straight away. I recommend that you do the same using the definition so that you get familiar with the
Okay.
definition. Do quite some problems using the definition also. Okay.
Okay, ma'am. I actually completed all the AQs, so I'll go over all those with the definition as well. Then.
Okay.
Thank you, ma'am. Yeah.
Okay, fine. So let us continue. So let f from R2 to R2 be a function given by f of x comma y is equal to p of x comma y comma q of x comma y. Okay. So you are now having two functions inside a function. It is not any big deal. Whatever you have done here, they have just given some names. That's all. So for example, you are having a function, maybe where is this functions? Any multivariable functions, vector valued functions. I don't see any vector valued functions. Maybe it was in the beginning, I guess. Yeah. So for example, they are giving a name. For example, this is maybe F1, this is F2. Like this, they are giving a name. It is not any big deal. There are not too many functions, just that they are giving name for each of the coordinate functions. Okay. Remember here, each of the coordinate is a function, and so we call it as coordinate functions. They are just giving some name for it. In this example, we are going to see. Okay. Fine. Where is that? Yeah. So here they are giving this first coordinate as P and second coordinate they are calling as Q. Okay. Now what is your, they are asking to find all this for P as well as Q, you have to find the partial derivative with respect to X as well as Y. So your P of X comma Y is 6X plus Y squared. What is dou P by dou X?
6.
6. What is dou P by dou Y?
2y.
And your Q of X comma Y is given as 3X squared plus 2Y. Now what is dou Q by dou X?
6x.
6X. And what is dou Q by dou Y?
2.
Is just 2.
2.
Right? Now before this, can you tell me, is it scalar valued or a vector valued function?
Vector valued.
Obviously, it is a vector valued function because your image is a vector. Okay, fine. So let us come back here. So now what is the matrix A? Can you tell?
6 2y.
6
2y. 6x 2.
X 2. And what is the determinant of this matrix A?
12 minus 12xy.
And that is given to be 0. So it means 12
XY
is
is
equal to 12xy. So what is the value of xy?
1.
1.
Okay, your xy value is 1. Okay. So whenever you see some problems like this, you see that it is multivariable and then matrix are there and then determinant is there, you feel that something big. But whatever problem is given, just read it. Maybe it is very simple. Okay, don't get alarmed or confused by the problem statement itself. Maybe it is very easy. So remember that always. Okay, fine.
Ma'am.
Yeah.
You said that it is recommended to use the definition instead of using direct derivatives.
Yeah.
Why, ma'am? Is there some
Not always.
contradiction
Not
by the
always.
derivatives?
Not always. I said when you are particularly having some case like this, a piecewise function where one part is only for 0, 0.
Yes, ma'am.
There, suppose you are having a function instead of 0 here. In that case, since it is for 0 at the point 0, 0, I recommend you to use the definition instead of writing the formula directly. Okay, not always.
Okay, ma'am.
Okay. Okay. So the next concept is, so far we see that, see in this graphs also you see that. So whatever we see here I am fixing the value of y and then finding the derivative with respect to x. And here I am fixing the value of x and finding the derivative with respect to y. But we are considering only two directions. You are considering the direction of x and then you are considering the direction of y. Okay. Now it can be in some other direction also you can find the derivative, right? When you are having only two coordinates, so you are finding with respect to x and with respect to one direction x and y. Now you can also consider any other direction also, maybe along some particular point given to you. Okay. So mainly that point, what you want to consider is as a unit vector. What you need is a unit vector. Okay, that is what is going to help us also. Remember that when considering the direction of x-axis and y-axis also, we consider the unit vectors along x-axis and y-axis. What are the unit vectors along x-axis? Unit vector along x-axis.
1 0.
It is 1, 0. Same way, unit vector along y-axis is
0 1.
So this is E1, this is E2. That is why when you are finding the derivative along x-axis, you are considering the unit vector E1. And when you are considering the derivative with respect to y-axis, you are considering the unit vector E2. Okay. Now we are generalizing this for any given direction. Consider the unit vector in that direction. That's all. So in the directional derivative case, the rate of change in the direction of a unit vector in the specific direction you are asked to find the derivative. Okay, so du of f of x1, x2, xn is the directional derivative of f at the point x1, x2, xn in the direction of the unit vector u. Okay, so how do you read this? The directional derivative of f at the point x1, x2, xn in the direction of u. Okay, so now this you see that limit h goes to 0, f of x1 plus u1h plus x2 plus u2h plus etc. xn plus u1h. Basically here what you have done, f of, let us call this as x tilde plus h times of u minus f of x. This expression only is written in this way. Okay, so here earlier we had any some ei. Now instead of ei you are having some unit vector u, that's all. Okay, so this is what is called directional derivative. To find the directional derivative of a function in a particular direction, we first have to find the unit vector in the direction, and then you compute this directional derivative. Okay, so as I told you, partial derivatives are special cases of directional derivative when u is equal to ei. That's all. Okay, so directional derivatives are generalizations of partial derivatives, or you can say they are partial derivatives are special cases of directional derivative. Okay, so now look at this statement. Which of the following statement is or are true? The directional derivative of f of x comma y at a point a comma b in the direction of a unit vector u is a non-negative real number. Is this true? See, what about partial derivatives? Are they always non-negative?
No, ma'am. It
No,
can be
ma'am.
negative as well.
It can be negative also, right? So if
Yeah.
partial derivatives itself can be negative, then directional derivative also can be negative, right? Because
In the opposite direction.
yeah,
Yeah.
okay.
Yes, yes.
So this statement is wrong. This can be this directional derivatives can be any real number. Of fx, and this can be any real number. Okay. The directional derivative of any function is always a scalar. Is that true?
Yes,
Yeah.
ma'am.
Yes,
Ah,
ma'am.
yes, true.
Only if it is at a specific point, yeah. So you are given directional derivative of f at some specific point, yes, then it is always a scalar. Okay, so directional derivative, you see, you are always finding the direction at some in some specific direction, so it is always a scalar. Okay,
I mean, general derivative itself is a scalar, right? Or
see, it is scalar valued, but it is not scalar. It is scalar valued.
okay, what I'm asking is, will the, I mean, do we get vectors as a derivative anywhere?
No.
Okay.
Okay, fine. Okay. So far, yeah, here one thing we are considering only scalar valued functions. That is why only scalars are coming. We are not talking about vector valued functions. Okay, whatever definitions we have seen so far, they're all scalar valued functions. Remember that.
Oh, okay. Maybe in case we go for
Yes.
vector valued function,
Yeah,
the
yeah.
derivative will also be a vector. Okay.
Yes.
Ma'am,
Okay.
in the second option,
Yeah.
you told that the directional derivative of any function is always a scalar at a particular point.
See, it means that, see, always directional derivative itself, we are finding in some specific direction. That is the definition of directional derivative itself, right? So, for example, here you see, you take one particular vector. Okay, u is one particular vector, and in that vector, you are finding the number value. Okay, so that is why directional derivative is always a scalar. Here, for example, you see this partial derivative with respect to x. I'm finding for any x comma y not equal to 0 comma 0. Okay, and this directional derivative, I'm doing it only for a specific direction, and this u is here. Okay.
Okay, ma'am.
Fine.
Okay, fine, ma'am.
So directional derivative of any function at a point, you can say at a point is always a scalar, or you can say it is scalar valued. Okay, the rate of change of f of x1, x2, xn in the direction of a unit vector u, a1, a2, an is called the directional derivative of f in the direction of u.
True, ma'am. That's
True.
the directional derivative
Definition.
definition.
Yeah.
Yes.
So in the direction of a unit vector is the directional derivative. That is the definition itself, right? Okay.
Yes.
The directional derivative of any function is a vector because it is dependent on the direction of the unit vector.
No, ma'am.
No, ma'am. No.
It's never a vector, right?
Yeah, it's not a vector.
Okay, fine. Now let us look at this case. The rate of change of f of x comma y equal to x plus y at 0 comma 0 in the direction of the line y is equal to x. So what are all the points along the line y is equal to x?
1, 1, 0, 0, 1, 1,
1,
2,
1.
2, 3, 3, and so on.
1 comma 1 is a point. Any other point?
2, 2, 3, 3, 4, 4.
0, 0.
See, any value is any point is of this form x comma 1.
X,
So x comma x.
yeah.
Okay. So x comma x is the general point on this line y is equal to x, and you have to find the unit vector. Remember, for finding the directional derivative, the first thing is that finding the unit vector along y is equal to x. Okay. So it means take any point of this form x comma x and find the unit vector along that line. Okay. So here, if you are taking 0 comma 0, then you won't be able to find the unit vector. So we don't consider the 0 vector to find the unit vector. You consider any non-zero vector. You can either take x comma x itself, or the easier case is 1 comma
1.
So 1 comma 1 divided by
1 by root 2.
Root of 1 plus 1.
Yeah.
So it
Root
is
of 2.
1 by
1
root
comma
2,
1 by.
or you can write it in this way also.
1 by root 2.
So this is a
1 by
unit
root 2,
vector along y is equal to x. Okay, fine. Now, what is the rate of change of f of x comma y equal to x comma y? So let us use the definition now. What is the definition? Du of, now you are having only two variables. So let us write it. Du of, here your u is 1 by root 2, 1 by root 2. So what is du of f? Du of f is limit h going to 0, f of your
X plus 1 by root 2.
x1 plus u1h. So x1 is x here plus u1
h by root 2.
by root 2. So h by root 2. Okay. And same way y plus h by root 2. The whole divided by h. Okay. Now what is limit h going to 0 f of x, at the point, at which point?
Minus f of xy, is it not required?
Sorry?
Minus f of x comma y.
Sorry, I missed that point. Yeah, minus f of x comma y. At which point you are finding?
0
At
comma
the point
0.
0 comma 0. So it means limit h going to 0, f of 0 plus h by root 2, comma 0 plus h by root 2 minus f of 0 comma 0 whole divided by h. Okay. Now what is f of h by root 2 comma h by root 2?
H by root 2 plus h by root 2.
So 2h by root 2, and f of 0 comma 0 is 0 plus 0, so 0 whole divided by h. Now this is limit h going to 0. So 2 by root 2 is root 2 times h by h. So you are having limit h going to 0, root 2. So answer is root 2. Is it okay? Okay. Now instead of y is equal to x, in your video also the same y example is given. So I'm asking you, maybe suppose you are asking the same question in a different direction. Suppose let us say y is equal to 2x. Then what will you do?
In the DD, I'll change it from 1 comma 1 to 1 comma 2.
So you find what is the unit vector along this y is equal to 2x. Then what is that? It is
it will become 1 comma 2, and the DD will become 1 by root 5 and 2 by root 5.
Okay.
Ma'am, please explain DUF once x plus h by root 2, y plus h by how it.
So, okay, I will write the definition for you here. So, what is the definition? The definition is that limit h going to 0, f of x plus h u1 x and then y plus h u2 minus f of, here f I missed, f minus f of x comma y. So what is your u1 and u2 value? This is your u1, this is your u2. So h times of u1 is simply h by root 2 and h times of u2 is simply h by root 2. Is it okay now?
Okay.
In this definition, you see x1 plus u1h. So your x1 is nothing but your x here. Okay? Your x1 is nothing but your x here. x1 is x and x2 is y. And the remaining things are same. Only two coordinates are there, so we stop with two coordinates. Is this okay now?
Okay, ma'am. Is there any proof for this formula, or just we have to remember it?
Is there any
Proof for this? Do
proof?
you have? Yes, ma'am.
This formula?
Yes, ma'am.
What kind of proof you are asking? I don't understand.
Ma'am, derivative.
How it?
Yeah.
So for this, how to verify you are asking?
Yes, ma'am.
Only way is to do this steps only. So there is another method using gradient which you will see later. Okay.
Okay.
So for now, only this method. Later on, when gradient topic comes, you can see that. Okay. Fine.
Ji, ma'am.
Ma'am, if we
Ma'am,
take any other
just
vector,
Yeah.
sorry, if we take any other vector also, we'll get the same answer, right? Like instead of 1, 1, 3, 3 or 5, 5, we'll get the same root 2.
Yeah. For example, if I take this x comma x itself, then x comma x, you say x comma x by square root of x
2
squared plus x squared. So what is
2x
it you
square.
are getting? X comma x by square root of 2 times of x. X
square.
and x gets cancelled, so you get 1 by root 2, 1 by root 2. So
Okay.
same way here also, if you take x comma 2x, any point satisfying this condition, it can be 2 comma 4 or any other point, the unit vector, you will get the same value. Okay.
Okay, ma'am. Thanks.
Ma'am, it is required to take x comma x.
Yeah, any vector of this form x comma x, any non-zero vector of this form x comma x.
It is predefined x comma x.
Because here
No,
y
it
is equal to x.
y is equal to y.
Yeah.
Okay,
X is
so if
So
it is
y-
y equal to 2x, you have x comma 2x. In place of y, you have 2x. Okay, fine.
So we can take in the form of y comma y also.
See, it does not matter y or x. Y comma y also is fine. Okay, as long as both the coordinates are same, it's fine.
Okay, ma'am.
Okay, so now the rate of change of f of x comma y comma z equal to xy plus yz plus zx at 1 comma 2 comma 3 in the direction of the vector 4 comma 3 comma 0. How do you find this one?
Now, instead of just two variables, there are three variables given. So we'll say.
So now you see
x1.
that what is your u and what is your value x naught, y naught, z naught.
U is 1 by 5, 430.
So this is your x tilde and this is your, this contributes to your u. From this, how do you find your u?
1 by
1 by 4 square plus 3 square.
square root. Yeah.
And square root. 16 plus 9, yeah, 25, 5. So 4 by 5, 3 by 5.
Okay, 4 by 5, 3 by 5, and then 0. So these are the coordinates you are having. This is the unit vector along this direction. Okay. Now, if you are using the definition du of f at the point 1 comma 2 comma 3, then it is limit h going to 0, f of first coordinate is 1 plus h times of this coordinate.
4 by 5.
4 by 5 times of h. And then 2 plus 3 by 5h. And then 3 plus 0. Minus f of 1 comma 2 comma 3 whole divided by h. Okay. Is this form? I have just straight away applied the formula. Is this fine for everyone?
Yes,
okay.
Yes, madam.
Fine. So next, limit h going to 0. What is this now? If I'm writing it, 1 plus 4h
by
4 by
5,
5h into
2 plus 3h by y.
5h, and then plus 2 plus 3h by 5 into 3 plus 3 times of 1 plus 4h by 5 minus, for this what is f of 1 comma 2 comma 3?
2 plus 6
2
plus
plus 6
6
plus
plus 3.
11, right? Whole divided by,
H.
okay. So limit h going to 0. Here now you have to do this multiplication. So 2 plus 8 by 5
8
times
minus
of
11.
h plus you have
12h by
3h by
5.
5 plus 12
12h by
h
5.
squared by 25
5.
plus 6 plus 9h by 5
Right.
plus 3
3
plus 12h by
12h by 5.
5 minus 11. So just let us first look at the constants. When you are looking at the constants, what are the terms you are having? 2 plus 6 plus 3.
8, 11,
11.
0.
So 11 minus 11 is 0. So these terms will contribute to 0. Okay. So you have limit h going to 0. These terms are becoming 0. So I'm taking
H
h
take
common
out
to
that,
the
yeah.
remaining terms. Yeah.
Yeah.
So
32,
first
I
of all, let
guess.
us add these terms. What is the sum of these terms?
11,
Where you are having
20,
h.
32. 32.
So you have 11, 11 plus 9, 20, 20 plus 12, 32. 32 by 5. And then
Plus
what is
12
the
h
other
square
term?
by plus 12
12h
h
by
Plus 12h square by 5.
25.
Is it not h square?
H is taken out.
Okay, h is taken out, yeah.
So now when you are applying h going to 0, what is the answer?
32 by 5.
32 by 5.
It is 32 by 5. Okay. Fine. So the next question is a little different. Instead of giving a specific direction, they are giving in this way. Straight away, they have not given. They have, of course, given a specific direction, but they have not given it straight away. Okay. The rate of change of f of x comma y equal to sine of x comma y at 1 comma 0 in the direction 60 degree from the x-axis. Okay. It means what? You are at this point 1 comma 0. Okay. Now this vector, okay, you are rotating to an angle of 60 degrees. Okay. So now what will be this this value now? This point
Root
now?
3x. Y is equal to root 3x.
Yeah.
Cos
What are the
60,
coordinates?
cos 60, sin 60.
Yeah. Cos 60, sin 60. Okay. Suppose if it is given as 30, then
Cos 30, sin 30.
cos 30, sin 30. That's all. Okay. Remember here we are moving the line 1 comma 0. If you are having some other value which is not a unit vector, then you have to find the unit vector along that direction. Here you are directly given a unit vector, so you don't have to worry. Straight away cos 60, sin 60 you are doing. Okay?
Ma'am, actually it is a line passing through origin having slope 60 degree.
Yeah.
You
Okay.
can say.
Fine. So cos 60, sin 60, what is this value of this cos 60, sin 60?
1 by 2, root 3 by 2.
1 by 2
Root
and
3 by 2, comma 1 by
3 by 2.
root 3 by 2, comma 1 by 2.
I guess
the other way
1
around.
by
No, what you
Root 3
wrote
by
is
2.
Cos 60 is
no,
1
no.
by 2, ma'am.
1 by 2. What you wrote first was the right.
1 by 2 is the first one. Yeah.
1 by 2, ma'am. First one.
Yeah. I'm also getting confused when you say, okay, fine. So this was the correct answer. Okay, fine.
What you said about that unit vector, what if the point was given as let's say 5 comma 7 instead of 1 comma 0? What should we do?
See, then if it is first of all 5 comma 7, if it is see, from x-axis they have given, that is why finding the coordinates is very easy. You already know that when you are moving a point from this x-axis, it is just the coordinates are cos theta and psi theta. If it is some other point, then first of all 5 comma 7 you have to convert to unit vector, and that unit vector when you are shifting to first of all it is already making some other angle. So from where it is from x-axis or from different axis, those things you have to first use the Pythagoras theorem and find the coordinates. Okay, so that is quite involved. So usually I don't think that kind of complicated things will be there, but it is good to know that in that case you should use Pythagoras theorem to find the coordinates. Okay. Fine.
Okay, ma'am.
Madam, can you explain this a little bit more in detail? This
Which one?
current problem. This same problem.
This one?
Yes.
See, here what is happening? You are first of all having this point 1 comma 0. Now they are asking to find the rate of change of this function sin xy. So in the direction 60 degrees from this point 1 comma 0. So 60 degrees from 1 comma 0 means you are at the point cos 60 comma sin 60. Okay. When you are doing a rotation on the unit circle in the previous chapter in the rotation matrix, we have seen that this point is nothing but cos theta comma sin theta, right? So now you see that here this vector is it a unit vector first of all, cos theta comma sin theta?
Yes, ma'am.
Any cos theta sin theta is a unit vector, right? Because cos squared theta plus sin squared theta is 1. Okay, so straight away, so you can use this point as a unit vector in this direction. So your unit vector is this.
Okay.
Okay. Shall we continue doing the problem now?
Ma'am, have you taken 1 comma 0 because of we have to calculate unit vector in the direction of?
No, it is already given at 1 comma 0 in the direction 60 degree from x-axis.
If it is given 5 comma 0, then
if it is given 5 comma 0, then anyway going to theta is going to come along the same direction. So first 5 comma 0 I will convert to 1 comma 0 and then I will consider the 60 degrees from there to get the unit vector. Okay.
Ma'am, I think that point is different, right? But the angle they are referring here is from the x-axis. Even if they have given at 5 comma 7 in the direction 60 degree.
Yes. At 1 comma 0 because it is from the x-axis. Yeah, correct. Yeah.
Yes,
from x-axis because 1 comma 0 because it is from x-axis. Yeah.
We have followed the same process if it is given 5 comma 0 as well.
Yes.
At 5 comma 0 you have to follow the same procedure. Yes. Sorry, I told something wrong. Yeah. So from x-axis means you are considering from 1 comma 0. This 1 comma 0 has no relation between this point
Yes,
1 comma 0.
We have taken 1 comma 0 because of we have to calculate unit vector.
Yeah, from x-axis. Yes.
Yes. Okay, ma'am.
Okay.
Thank you.
Fine. Now, what is the formula? You have to find du of f at which point 1 comma 0. So this is nothing but limit h going to 0 f of x value is 1, so we'll write 1 plus h times of 1 by 2, so h by 2 you can write, and then you have 0 here, so you have 0 plus
root 3 by 2h.
Root 3 by h by 2. Root 3 h by 2 minus f of
1 comma 0.
the whole divided by h. Now this is equal to limit h going to 0. What is this sign of? 1 plus h by 2
into
root 3 h by 2 minus f of 1 comma 0 is
0.
Sin 0. And what is sin 0?
0.
0. Okay. Fine. So now you have to find limit h going to 0 sine of this value by h. So you have limit h going to 0 sine of 1 plus h by 2 root 3 by 2. Here you have sine 0 is 0, so the whole divided by h. Now, what is the next step? Can you guess?
Multiplication 1 plus h by 2 into root 3 by h2.
Divide numerator and denominator by the argument of sign.
So here it is difficult to find the limit when you are having it in when you are having this variable inside a function. So whenever you are having a variable inside a function, then what is the rule you use? What is the rule you use?
L'Hospital.
Yeah. So if you are using the L'Hospital rule, then what is that you can do here? You consider this as a function and then first find the derivative of this. Same way you find the derivative of this, right? Now, if you are considering this as a function of h, maybe since f is already here, maybe I write some other function. Maybe I'll write it in a different color. So let us say g of h is this function sine 1 plus h by 2 into root 3 by 2h. Remember, these two values are together inside sine. Okay. So now what is g dash of h? You have to use chain rule, right? Because variable inside a function. So function inside function. So
can't we multiply those two?
Yeah.
We can't multiply those two. 1 plus h by 2 into root 3 by h2.
Yeah, you can multiply, of course. So if you want, you can multiply and rewrite it as sine of root 3 by 2 times of h plus root 3 by 4 times of h square. Okay. So now applying chain rule, what is that you will get?
Cos
Cos of this function and then into
root 3h, root 3 by 2h, root 3 by 2 into plus
root 3 by 4.
2 root 3 by 4.
2 root 3
2
by
root 3
4.
by
So
4
which
h.
is root 3 by 2h. Is that fine?
Yes.
Yes, ma'am.
Okay. Now you are having this is equal to, let us replace this term here. So when you are replacing this term here, you will get limit h going to 0. Here you have now cos of root 3 by 2h plus root 3 by 4 h squared into root 3 by 2 plus root 3 by 2h. Okay. So now you are having only products, and now when you are finding the limit, what is g dash of 0 down? What is the value g dash of 0?
G dash 0.
It is
3 by
cos of 0.
Oh, cos 0.
Root 3 by 2.
Cos 0.
And what
Plus
is cos
0.
0?
1.
1.
1. So the answer is
root 3 by 2.
Root 3 by 2.
okay. So here your answer is root 3 by 2.
What about the divided by h?
So here for this also we are taking the derivative. Just like we took the derivative of this, we are taking the derivative of this. So you have divided by 1.
Okay.
Ma'am, just a quick question.
Yeah.
When we are given points, so then we convert into unit vector.
Yeah.
So now we have given angle and we have direct written the points. Why it is so, ma'am?
Here, as I told you, here this point cos theta comma sin theta is already a unit vector. That's why I have taken straight away this value cos theta comma sin theta as a unit u. Did I answer your question?
Oh, yes, ma'am.
Okay. Fine.
Ma'am, for that sine function, you said you cannot directly apply the value h tends to 0.
Is it no, it is sorry, it is not because it is of the sine function. You have divided by h. So using the u by h, yeah, You have 0 by 0 form maybe. Sine 0 by sine of 0 into 0 you will have, I guess. So you have
Okay.
0 by 0 form. To avoid that, you are using L'Hopital rule, not because it is inside the sine function.
Okay.
Okay.
So
All right. So
to make the denominator something else,
yeah.
okay, you're doing that.
So whenever you, I guess in L'Hopital rule, there are few conditions under which you do this. So sine of, sorry, not sine of, limit h going to 0, some function is you are having numerator and denominator you are having. And when you are applying 0, if you get both the numerator and denominator in the form 0 by 0, then what you do is that instead of finding the limit, maybe I write it somewhere here. So maybe in a different color. So you see limit h going to 0, f of h by g of h. Okay, it is same as limit h going to 0, f dash of 0, or f dash of h by g dash of h. Okay, so when you are applying this, if it is in the 0 by 0 form, then you can use the L'Hopital rule. This is what we have done here. Okay.
Okay, ma'am. Okay, thank you.
Okay, so I guess there are still some more problems left. Maybe we can continue in the next class. Okay. So far, what are the topics we have covered? Mainly, we have seen what is partial derivative. First, we see what is rate of change, and rate of change at a specific point we see, and then we see rate of change in a specific direction. That is nothing but your partial derivative along x or y axis we have seen. And then if you want to consider the derivative along any direction, that you call as the directional derivative. Okay. So these are the things we have seen so far. In the next class, we will do more on directional derivatives, and then we also will see about limits and continuity for multivariable functions. Is that fine?
Okay, ma'am. Can you please provide PDF in the chat box?
Provide PDF.
Yeah, this
ma'am,
PDF.
this PDF.
Okay, let me see.
Actually, some of the PDFs are missing. Some of
Yes,
the
madam.
Only one
previous
PDF, I know it is not up. I did not provide. I told you it is crashed, but other PDFs should be there. Which PDF is not there? Can you tell?
I guess week 7 was